Hello, and welcome to another lecture. We're looking at exact equations today, or at least part one of this section. And the section is 1.8, and you can get the book for free at this URL, or you can buy an inexpensive paperback if you want. So, all right, so what are we looking at? We're looking at exact equations. So what are exact equations? Exact equations are equations that encode basically this thing. They encode, given a function f of two variables, let's say, let's just do everything in two variables. So we have f of x and y, and we want the uh, the uh, the level sets of this function to be the implicit solutions for these differential equations. So basically, for different constants, if I plug in some constant, I get some implicit solution, right? That's basically what we want to encode by exact equations, right? So these are the solutions, right? So we're gonna do first to explain what they are. We're gonna sort of start backwards. We're gonna start with the solution and get the equation, but then later on we're gonna do the thing in the correct order once we understand what these are, right? So basically, that's what we're looking at. We're just looking at functions where the level sets of the function are the solutions, the implicit solutions. All right, so this f this one is called a potential function, and the naming sort of suggests and really comes from these things come up when you have something like electric potential or potential energy. So and it these sort of equations come up usually when you have some sort of a conservation law at play, such as conservation of energy. So that's often when you get these equations or these sorts of equations. All right, so let's look at an example. And again, I'm saying we're sort of going backwards. This thing is going to be sort of the solution, right? But we want to figure out how that how that works with the equation. So how do you encode this function, right? So what do I mean by level sets, right? So for example, here the function is x squared plus y squared. If I look at where x squared plus y squared is constant, those are precisely circles in the plane, right? So it's it's a circle centered at the origin, right? And square root of c would be the radius, right? So that's what we should be getting, right? And those are those would be our implicit solutions, right? But we don't know to what equation yet. Well, to get the equation, let's differentiate. So if we differentiate f, some function of two variables such as this, right? We will write it as ds. We're basically just taking the partial derivatives, but there's two partial derivatives, and so we write what you in multivariable calculus you call it total derivative, and that just means you take the partial derivative with respect to x, multiply by dx, plus the partial derivative with respect to y, multiplied by dy. Now, another way that we're going to write these things is it was a subscript notation. I mean, that's the same thing. This thing over here is the same thing as this thing over here, right? It's just a different way of writing it. If you're a little lazier, you can write just f sub x. It also doesn't take up so much space, right? So that's the total derivative, right? Just really a way of writing down the derivative, right? So for example, in this case, when it's x squared plus y squared, the total derivative f is 2x dx. That's the derivative with respect to x, plus 2y dy, which is the derivative with respect to y, right? So what do we do now? We want to encode this this function, this equation, sorry. So you want to encode when is f a constant. Well, if we differentiate, if we do total derivative of a constant is 0, right? So what we really have is that df is 0, right? That's the equation. That's the differential equation. That's going to be our exact equation. So in this case, it's going to be this thing, the total derivative of f, 2x dx plus 2y dy equals 0. Another way of writing that could be, I could divide by the dx, basically. So you write it like this, in which case this looks more like the type of equation that you've seen up to now, right? Where you have just the derivative of y with respect to x in the equation and just some x's and y's, right? So, all right, so that's the equation. Usually we start over here and we want to get here, right? We don't do the opposite, right? We start with an equation and we figure out what that capital F should have been, right? So, in general, you start with something like this, where m and n are functions of x and y, right? Just some random functions of x and y. And so, you could write it like this. And really, any first order ODE, which is dy dx is something. I mean, you could write it like this somehow, right? So, just being of this form is nothing special, but it's exact if it actually is an equation of this form. If this thing is df equals 0. So what does that mean? That means that this guy is exact if there exists an f. So if there exists a solution where m is the x derivative of f and n is the y derivative of f. And it's not always true. You can't just start with any random m and n and find an f where this works. All right. So in this case, yes, this is exact because we got it from the solution, right? So again, we were going kind of backwards, right? And this, where f is equal to c, those are the implicit solution. And this c, that would then be the the constant that if you have some initial values, right? That's the constant that you solve for, right? So you're getting these sort of implicit solutions. In this case, you can also find these explicit solutions that sort of looks more like what you would you would see normally, right? You start something like this and you end up with something like this. All right. So normally the idea is to start with something like this and try to find an f, right? That's the that's the thing. Now, before we get to trying to actually solve some equations, let's look at a certain interpretation of this. A certain interpretation using what you've learned in multivariable calculus. So if you don't remember your multivariable calculus, maybe this slide is not going to make so much sense. But hopefully, for those of you that had multivariable calculus, this might bring it together with something that you've seen, right? So if I look at these functions m and n, and I think of them as a vector, right? So it's a vector that points somewhere, right? This has a x component and a y component, and so that gives me a vector field, right? Now this vector field v mn is a conservative vector field. Well, if it comes with a potential function, right? And if you remember, you also called it the potential function, among other things. When you looked at conservative vector fields, so that's it's something that you've probably seen in multivariable calculus, right? And it uses the same terminology, except it's conservative vector field instead of an exact equation, but it's actually the same thing, right? Now, something that you've probably also looked at when you looked at conservative vector fields is well, I mean, you could, if you think of v as a force, right? Then you can the path integral of v is the work done, right, by the force, right? So the work required to like move a box up the stairs, right? It's if you're maybe thinking of the force of gravity, right? So to move it up, requires certain work, right? And that's given by this integral, by this path integral. And a conservative vector field if you have this potential function, right, the work done is just actually difference in potentials, right? Because you can actually apply the fundamental term of calculus. So you will get that the work done is actually just the difference in the potentials from the starting point to the ending point, right? Um, so, for example, if you're moving a heavy box up the stairs, you think that it's more work than taking the elevator, but it's actually the same exact work. It's just that the elevator does the work if you move it up the elevator. All right. So force of gravity is conservative. I guess here we're assuming 2 dimensions, so we're kind of in the flat world. Normally you have 3 dimensions, but it's the same idea. And F would be the gravitational potential, right? And so work done, as I just said, it only depends on the change in elevation, because the gravitational potential only depends on the distance from the center of the Earth, right? So exact equations are conservative vector fields, and their implicit solutions are the potential functions to these conservative vector fields, right? So that's basically where that's where it ties into what you've already seen in multivariable calculus. Okay, so let's get back to differential equations. So the process of what's what would generally happen here is that we somehow get an equation that we want to solve. We first determine, and we're going to have a test for this before, so that we don't have to start solving if we can't, right? We determine if the equation is exact. It's actually fairly easy to figure that out. And if it's not exact, then there's no point in trying to solve. And if it is, then we try to solve. Then we try to find an f such that f sub x is m and f sub y is n. And it really sort of is that simple. We essentially just figure out, well, how do we do this? And then once we have that, how do we do this, right? And then you get an implicit solution like this. All right. Now, adding a constant to f doesn't really change anything. It's the the absolute value of the potential is not really doesn't really make a difference. I mean, you can if you're measuring voltage, right, you're always measuring the difference between 2 points. So you have to have in the voltmeter you have to have 2 probes. You have to be measuring difference, right? So it's only differences between points that make a difference. So adding a constant doesn't really change anything, and you can sort of see it on the on the equation. If I add an f to add a constant to my f. So let's say it's f plus 3. Well, when I take the total derivative, the 3 just disappears. So it should be the same thing, right? So we're not really going to get one potential function. We're just going to get one of the potential functions, right? And it's really only up to a constant. All right. So let's start with this, and let's forget that we actually knew what f was. I mean, we know what f was, but let's forget that. Let's suppose that we didn't know this. It's been too long ago. We don't remember what it was, right? How do we get an f? Well, we have that m is 2x and n is 2y. So if f exists, and we're hoping that it does. I mean, we know that this is an exact equation, so it does actually. So we have to have that f sub x is 2x, right? So, well, that's just the derivative in x is 2x, so we can integrate in x. Now, if we integrate in x, we get, well, 2x, the antiderivative is x squared, right? And then we get some constant of integration. Now, the constant of integration is not constant. It's only constant in x, so it does not depend on x, but it could depend on y. For different y, you could get a different constant of integration when you're integrating in x. So that's why we write f as, well, whatever it is, it's x squared plus some function of just depending on y, not on x, right? All right. So now, well, that means that that we're getting the 2x. We're getting that this thing, right? So we also want the other guy. We want that f sub y is 2y, right? So we want this. So we just do it. We take the derivative of, well, we know that f has this form, and we take the derivative with respect to y. So that means treating treating x as constant and differentiating in y, and a is just a function of one variable. So we just get a prime in this case, a prime of y, and that's supposed to be 2y, right? Well, so I can figure out what a is. I know that a prime of y is 2y, so I can take y squared. And you don't really need a constant of integration in this case. If you add it, that just means that you're getting a different potential. It's like basically you're just adding a constant to the potential, and we just said that that doesn't really matter, right? So you don't really need one. Okay. So in that case, so what do we have? F is x squared plus a of y, and we just figured out that a of y should be y squared, so it's x squared plus y squared. And if we added a constant of integration, we'd get that here. But again, as I said, we don't need it because we're looking at where this is constant. So we're basically adding a constant of integration when we're looking for the different level sets of f. All right. So the procedure, if the equation is exact, is integrate f sub x equals m in x, and I will have something, whatever the integral is, plus the constant of integration, where the constant of integration depends on y, right? Then you differentiate this thing in y, right? So that something will differentiate. It doesn't need to drop out like it did in our example. Maybe something more complicated. So you get something, and that something is supposed to equal n, right? And so you look at that equation and you solve for a, right? You're gonna get a prime in there, right? So you really have an equation for a prime, right? So then you have to solve by integration, right? Okay. And roles of x and y, and so m and n can be switched, right? I mean, this is completely symmetric. You don't have to start with x and go to y. You can start with y, right? F sub y equals n, and then get to m. That's perfectly fine. All right, so let's look at something different, right? Something that we haven't seen. This thing. All right, so m is 2x plus y, and n is xy. All right, so we'll try as before. So suppose f exists, so then we have f sub x is 2x plus y, this m, right? And we integrate. So if we integrate 2x plus y, we get in terms of x, right? So we get x squared plus xy, and then the constant of integration, again, depending on y, right? Now we differentiate in y and set it equal to n. So n is xy, and we set it equal to the derivative in terms of y, which is x plus the derivative of a, right? Now, there is no way that this can be true. You cannot write x times y as x plus some function of y. There is no way to satisfy this equation. No matter what you make a prime of y, right? There's just no way. I mean, you could, for example, if you set y to 0, then the left hand side is 0, but the right hand side is not going to be 0, right? There's absolutely no way to satisfy this. So what's going on? Well, the equation is not exact, right? There is no such f, right? So we were supposing it exists, but it doesn't, right? So we can't find it, right? That's one way to figure out that the equation is not exact. It's to try to solving it, and if you fail, well, if you fail in this way, if you basically show that no, there's no way to do this, right? I mean, it could also be you failed because you can't do some of these integrations, right? All right. So how to check if f exists without I mean, one way is to actually try to do it, but without trying to do all these integrations, because they could be complicated, right? I mean, so far we've looked at very simple examples. So if f exists, then, well, this is true. That's the whole point, right? So if I take the y derivative of m, what is that? So m is the x derivative of f, right? So that would be the y derivative of the x derivative of f, right? And this is the way that we write it, right? Now we know that these guys, as long as you have sort of continuous derivatives, and we're assuming that all the derivatives are nice, you can take these derivatives in any order, right? You can take the x derivative first or the y derivative first. It doesn't really matter. You should get the same thing, right? So he gets this, right? Well, but that's the same thing as taking the x derivative of n, which is f sub y, right? So what we really get that if f is if the equation is exact, so if f exists, then you'd better get that the y derivative of m is equal to the x derivative of n. All right. Now it actually works in reverse with a small caveat. So this is a theorem by Poincare, is that if you have these nice, and they should be continuously differentiable, so the derivatives are continuous, m and n, and if you satisfy this equation, right, so this is equal to this, right, then near any point there is a function capital F which does the thing that you want, right? Now it's only local, so you might not get a global function, that works for all x and y. It's only for some x and y, right? Near any point, right? So near any point, you can find a solution, right? Maybe not globally. That's kind of tricky. We're gonna see an example of this, but locally you can. Right. So basically, that's what it that's the thing that you check, right? You check if the y derivative of m is equal to the x derivative of n, and then you can start looking for your f, right? Might not be able to find a global one, but you can always find a local one. You can always find the one that you're always looking for a solution to a differential equation near some initial point, an equation like this. So yeah, you will be able to find one there. All right. So okay, so I just said this. Now, back to this example where m was 2xy and n was xy. If I take the y derivative of m, I get 1. But the x derivative of n is y, and 1 is not equal to y. It's not exact, right? So we could have, we didn't have to do that integration, right? I mean, we're saving a little bit of work. Not too much work, but if it was a more complicated equation, you'd save quite a bit of work. It's much easier to differentiate than anti-differentiate, right? All right. So let's look at an example that maybe at first doesn't look like the type of equation that we've been looking at. So we're trying to solve this initial value problem, right? We have this this guy dy dx is this thing, and y at 0 is 1. All right, so we write the equation like this, right? And so m is 2x plus y, but now n is x minus 1. All right, well, m sub y is 1, right? Just like before. But n sub x is now also 1, so we're good. So this is exact, right? At least near the initial point, right? Or near any point, but not maybe globally, but definitely, we can start solving. So we integrate integrate m in x, right? So we're starting with here 2x plus y, so it's x squared plus xy plus a constant of integration that depends on y. We differentiate in y, so we differentiate this in y, so we're just going to get x plus a prime. That's this thing, and that's supposed to equal n. That's x minus 1. Right, so that just means that a prime is minus 1. So minus y will work for a, right? So again, you could add a constant of integration, but again, it's not necessary. So all right, so we had already had this. So now ay is minus y, so we add it in, and this is our f, right? So the implicit general solution is this thing, right? Now, we also want this to be true, right? So y at x equals 0 should be 1, right? So when x is 0 and y is 1, right, I should be, this should be satisfied. C should be whatever makes this true. Oops, sorry. So if I plug in 0 and 1 into this thing, so I get 0 squared, 0 times 1 minus 1, right? That's supposed to equal to C. Well, that's C is then minus 1, right? That's just because this is 0, this is 0, so I just get C is minus 1. All right, so C is minus 1. So we have, so it's really, this is the specific solution, not implicit. Oh, sorry, not explicit. Now it's implicit still, but we can solve this for y, right? So we can find an explicit solution now, and that's what it is, right? Okay, so that's fairly easy. Now, by the way, this thing is linear, so you could also have solved it, as you solve linear equations, right? Because you have this y here is only up to the first power, right? But it's actually maybe simpler than doing that. So, all right, but it's exact equations could be definitely not linear. So it happens that in this case it was a linear. All right, so let's look at another example. Let's look at so this looks slightly more complicated, right? So these are our m and n, and we have this initial value, right? So it's an exercise. It's a little annoying, but it's m sub y is equal to n sub x. It is true. It's not too bad. Just you have to m sub y, so you have to use quotient rule, right? And n sub x you also have to use quotient rule. But yeah. But here the example is this vector field, and it's a vector field that you may have seen. This is the vortex vector field. So it's not conservative in the entire plane minus the origin, right? So as long as you take the entire plane minus the origin, you're not gonna find an f that's defined. It's clearly not defined at the origin because that's where the denominator vanishes. So like you're dividing by zeros, like nothing really works there. But everywhere else, you can find an f, but not a global one, right? You can near any point you can find an f. We're gonna see it in a little bit, right? So the problem why you can't find why you wouldn't be able to find a global one is well, suppose that you let gamma be a circle. So this is going to again involve some multivariable calculus. So if you're not too familiar with that, maybe this is not going to make a whole lot of sense. But hopefully for those that have had multivariable calculus, they've actually seen this. I mean, I do this in class in calculus 3. So if you have a circle around the origin and just radius one circle, and you start at 1, 0 and you end at 1, 0. So you just go around the origin, right? And you do it, let's say, counterclockwise. Doesn't really matter at this point. So if f existed, then well, it should be it's work done by going somewhere and then ending up at the same place. So the work done by gravity on that object is zero, right? Because maybe it was hurting for a while and then it was helping, right? So it cancels out. So you should get zero if clearly if I take the f at the beginning and end point, which are the same one, then if I subtract those, I get zero, right? But that should be equal to this integral, right? That's the integral of the vector field around this circle, and well, that's just what this is. And if you work it out, and I'll let those of you that remember vector calculus or remember multivariable calculus to to compute this path integral. So let this be the unit circle. By the way, one hint is that on the unit circle, x squared plus y squared is 1. And so you're going to actually get 2 pi. Well, 2 pi is not equal to 0. Right? So this clearly, you cannot have an f that's defined everywhere here. That's nonsense. 2 pi is not equal to 0. But, there is an f defined near every point. We can still solve, we just cannot solve for a global one, right? So again, it's only locally, but that's fine. We're only interested near the point 1, 2. So as long as near that point, yeah, we're fine. And actually what we're gonna do is we're just gonna suppose that x is positive. And we're gonna do that because we look at this initial condition and x is positive there. So if we figure out a solution for positive x, we're good. We're gonna integrate m in x, or we could start with integrating n in y. And actually, if you just do one integration, if you integrate m in x, you will find arctan, and you will find that that's actually the same thing as integrating n in y. So this actually already works. You can double check that. So at this point that we could take the constant of integration here to be just 0, right? So skipping a little bit, but normally you would you would still go through that, but let's just go on. This is what the f comes out, right? This f actually works. So, and you can see where this is definitely not something that's defined everywhere, right? It's the I have y over x, so we're using x equals positive, so x is not 0, and arctan of y over x is not defined when x is 0, right? So all right, so we don't have a global f. We only have, well, locally, but actually on a fairly large set we get it for all positive x, but we definitely don't get it in the entire plane minus the origin. All right, so the implicit solution is going to be this. So the explicit solution is this thing. So you just take the tangent, right? Arctangent is the inverse tangent, right? And so so that's what we get. So what do we get? We actually get this. We get lines, right? So tangent of c, c is a constant, right? So these are just the slope of this line through the origin, right? So as y1 is 2, y1, so we get that tangent of c should be 2, right? That's the way that you're gonna satisfy this initial condition, right? So we have the solution is y equals 2x. Really simple one, right? And note that only for x positive, right? The whole thing kind of breaks down at the origin over here, right? So you kind of go through the origin, but it's this line. That's the solution, and here in red is the initial condition, right? So it looks scary, but it has a really simple solution, right? But again, not one that that exists globally, right? So, well, the f, this guy doesn't exist globally, right? You have to, like, if you had a different initial condition, if you had a condition, over here, you would have to, work a little differently, right? You can still solve near any point, but you have to get a slightly different f. Yeah, that's just what it is. All right, so, and actually, over here, if you were over here, you'd get the straight line going up. So you wouldn't be able to solve for y, right? So, all right. So let's end it here, and we're gonna look more at exact equations next time. So, all right. So see you then.